Hello, my dears. Here we will start, we will continue with the ammeter. In this lecture, we are going to study the multi-range ammeter, and after that, we will go to the voltmeter. There are two ways of connection for the multi-range ammeter. The first one is what you can see here in front of you, which is similar to the single-range ammeter, except we are putting more than one resistor in parallel, as you see here, and we are going to select one of them. So if you notice here, we have RS1 can be selected. So the ammeter will be only RS1 in parallel with the PMMC. Or we change the position of the switch. We are going to take RS2 with the PMMC. Or we will take RS3 with the PMMC and so on. So that's how we can get multi-range. This kind of connection is simple in terms of calculation, but it's having one small problem. The problem is we have to use a special kind of a switch here to avoid having overcurrent to the PMMC. Why this is going to happen? Let us assume that we are measuring a current of, for example, 1 ampere, and the PMMC has a limit, or the full scale deflection of the PMMC is, for example, 1 milliampere. If the case is like this, we are not supposed to make 1 ampere goes direct to the PMMC, otherwise it will burn it, it will kill it. So we will always keep resistor in parallel with the PMMC. Always we keep this resistor, like for example, we are going to have this connection, this resistor. So the 1 ampere part of it will go this direction and the rest will go there. What will happen if I open this circuit? If this circuit open, while it changing the position from this point to this point, in between, when I am in between, you will find the circuit is only having the PMMC. Only this is the circuit at that time, which means all the 1 ampere will go to the PMMC, which is going to damage it. That's why we need a special kind of a switch here called make before break. Means before you break with B, make connection with C. Before you disconnect C, make connection with D, and so on. That's what called the special kind of switch. We call it make before break to overcome this problem. The other connection, which is seen in the next slide, will not have this problem. Let us look at the other connection. This connection called Ayrton shunt, where we are keeping 3 resistors in series, R1, R2, and R3, and all of them in parallel with the PMMC. As you see, this is the PMMC. So I will select the range such that I will go to position B. If I go to position B, the ammeter circuit will be this one. This one. You see, this is the circuit of the ammeter. This is the PMMC, and in the same time, these resistors all going to be connected in parallel. How about if I go to position C? You are going to find only this resistor and this resistor in parallel, and the circuit going to look like this. At that time, RS will be connected with RS here, will be connected with the PMMC. We will see this after a while, but this Ayrton shunt, there is no point where the current will go to the PMMC without having resistor in shunt. There is no point to remove the shunt resistance. Always shunt resistance will be there. The shunt resistance, by changing the position, will be such that sometimes will be R1 plus R2 plus R3. Other times you will find R shunt is equal to R1 plus R2. Other times you will find R shunt equal to R1 only, as shown here. If you notice here at point B, when we are at point B in the previous figure, you are going to find that the shunt resistance will be R shunt is R1 plus R2 plus R3, and Rm only Rm, the meter resistance. If we go to position C, you are going to find that the total shunt resistance will be R1 plus R2, as I explained just now in the previous slide. What will happen to R3? It will be added to Rm. Similarly for point D or position D. When we are at position D, you are going to find that the only shunt resistance is R1, and R2 with R3 will be added to Rm as a resistance of the PMMC. Let us look at this example, which will make us more clear about the multi-range ammeter, especially when it's Ayrton connection, as you see here. A PMMC instrument has 3 resistors Ayrton shunt connected across it to make a meter as shown in the figure below. So we are having 3 resistors, R1, R2, and R3. The resistors are R1 0.05. This resistor is 0.05 ohm, where this resistor is 0.45 and this resistor is 4.5 ohm. The PMMC has Rm of 1 kilo ohm. The PMMC here having resistor of 1 kilo ohm. The resistor of the PMMC 1 kilo ohm. And its full scale deflection, again, this is the PMMC full scale deflection is 50 microampere, which means the maximum current can go here is 50 microampere. What he wants here, he said calculate the 3 ranges of the meter. So all what we need to know here is the range, only the range. Means what is the maximum current can be measured at each position. When we are at position B, what is the current allowed to enter? When we are at position C, what was the current allowed? And same thing with position D. So in the solution of this question, we are going to start with position B as seen in this figure. So if the pointer or the switch connected to point B as you see here, how the circuit going to look like? It's very clear that we are having R1, R2, and R3 all acting as a shunt with the PMMC. So we are going to calculate according to this point. So at that time, to calculate Vs, which this voltage, it's to be calculated as a Im into Rm, 50 micro into 1 kilo equal to 50 millivolt. That means the voltage at this point equal to 50 millivolt. Now let us calculate Is. Is is the current going to the shunt. Okay, how to calculate it? It's Vm divided by the total resistance. So it's Vm or Vs. We call it Vm or Vs, either one. Vm means the PMMC voltage. Vs is the shunt voltage, which is the same. Vs over R1 plus R2 plus R3 calculated to be 10 milliampere. Right now, we know that the current here, I found that the current going to this direction is 10 milliampere. And also the current going to this side is equal to 50 microampere. That means the range to be measured, which this current equal to both 10 and 50, 10 milli and 50 micro. 10 milli and 50 micro, which will be equal to 10.05 milliampere. Now what will happen if we change the position? If I change the position, some changes going to happen. Let us see what are they. So the position right now is this one. This is the position. Okay. At that time, to calculate Vm or Vs, it's not equal to 50 micro multiplied into Rm, because Rm comes, look, let me put it in with color to help you to understand. This is going to be the PMMC, and it's going to go through this resistor back to this point. This is the connection, if you notice. That's how the connection. And the shunt, I will make it with different color. This is going to be the shunt, this resistor and this resistor. So now when I calculate Vs this time, it's going to be between this point and this point. This is Vs. So what is Vs? It's equal to 50 microampere multiplied into Rm plus this resistor, which are R3. I hope you catch this point. So this is what's seen here. Vs is equal to Im into Rm plus R3, because R3 now included in the circuit of the PMMC, which equal to 50 micro into 1K plus 4.5 ohm, which equal to 50 millivolt. So the voltage here equal to 50 millivolt approximately. Now I can calculate IS. Why we are calculating VS? I calculate VS because I want to calculate IS, which is the current going here. So IS is equal to VS over R1 plus R2. This R1 plus R2 calculated to be 10 milliampere, which means the circuit is telling me now that 100 milliampere goes to this direction and 50 microampere goes to this direction. That means the current coming from here will be both of them. I mean 50 micro plus 100 milli equal to 10.5 milli, 100.05 milliampere. So I hope the idea is clear. Now before we go to the last part, we can look at it here. In the last part, when I look at this position, let me draw the new position. At the new position, this switch will be here. The contact will be here. So the circuit, if I can't do the circuit, I will find that the PMMC will be the blue color, the one I am drawing right now. This is the PMMC, including with it R3 and R2. And then it will go back to this. That's how the circuit is going to look like. How about the shunt? The shunt, of course, this resistor is the PMMC. The shunt will be only the red color, only this resistor. That's how the circuit look like. Now, what is VS in this case? VS equal to this voltage, which to be calculated as 50 micro multiplied into R total, where R total equal to Rm plus R3 plus R2. So if we do this, we are going to find the voltage here, this voltage. If we find this voltage, we will divide it by this resistance to get this current. And same as before, the two currents going to be the current N. So this is what he have done. He found VS, as I mentioned, this is VS, so equal to 50 millivolt. Then we will calculate IS, which equal to VS over R1. This time only R1 is the shunt, equal to 1 ampere, which means the total current will be 1.00005 ampere. Notice here he couldn't approximate. We cannot approximate because we want to calculate the value accurately. Now if I want to calculate the internal resistance of this multi-range ammeter, how to calculate it? The internal resistance Rn is equal to Rm parallel R shunt, which equal to Rm into RSH over Rm plus RSH. Or we can calculate Rn as a Vm over I range. That's how we can calculate Rn. So if you notice here, we are saying Rn equal to Vm over I range. We have three ranges there. That means we are having three internal resistance. Each range will have its internal resistance. Let us look at this example. A moving coil ammeter has a fixed shunt 0.02 ohm. That means this is the PMMC, and he said the shunt equal to 0.02 ohm with a coil circuit resistance Rm 1 kilo ohm. That means this resistance 1 kilo ohm, and need a potential difference of 0.5 across it for a full scale deflection. That means the voltage here, this voltage supposed to be 0.5 volt. Notice he didn't give us Im, but we can get Im. It's a very simple thing. So the voltage required is 0.5 volt for full scale deflection. What you want here, to what total current does this corresponds? So the arrangement or the 0.5 volt or this kind of volt will give me what range of current, means what is the current allowed to enter here at this situation. That's the first question. Then the second question, he said calculate the value of shunt to give a full scale deflection when the total current is 10 ampere and 75 ampere. So here we will calculate this value, it's no problem. But he said if I want to change this shunt to get 10 ampere, what will be the value of the shunt? Similarly for 75 ampere. To do this question, let me just draw it very fast here. We said we are having resistance here with the PMMC, I mean RM and the PMMC, and this is the shunt. Remember that he told me the voltage between this point and this point is 0.5 volt. So if I have this is 0.5 volt and this is 1000 ohm or 1 kilo ohm, simply I can calculate IM. IM is equal to V over R, which IM here equal to V over R equal to 0.0005 ampere. So this is the current flowing here, 0.0005 ampere. Now, what about IS? IS is to be, IS means this current. It's equal to the same 0.5 divided by R shunt. 0.5 over R shunt equal to 25. That means the current going in from here will be equal to 25 ampere, which coming here, 25, plus the current going to this side, which is this value. So when we add both of them, we are going to get the current at the input equal to this much, 25.0005 ampere. That's the first part of the question. In the second part, he said if I want to calculate the R shunt for a current of 10 ampere. Remember that we are having the circuit something like this. R shunt is not known this time. I don't know R shunt, but I know that the current here is 10 ampere. And the current here is calculated. This current cannot change. The current here cannot change because this is the limit for the PMMC. So we calculate this current earlier. Now I can calculate the value of IS, this current, which equal to 10 minus the current goes here. You see 10 minus 0.0005, which equal to 9.9995. I am talking about this current now. So this current is calculated. So notice that it's the same style. Always we are doing the same thing. If I have this current and I know this voltage 0.5 volt, 0.5 volt, we can calculate the resistance. So you notice here 0.0005 into 1000 divided by 9.9995 equal to 0.05 ohm. That means the current here equal to the current, the resistance, this resistance supposed to be 0.05 ohm to measure a current of 10 ampere. The same thing will be done for this range. So it's the repetition. It's the same thing, but we are repeating. So I will leave it for you. Now we will go to the DC voltmeter. What is voltmeter? It's the instrument which measuring the voltage. Voltmeter is instrument which measuring the voltage. For this analog voltmeter, we are using PMMC. The PMMC is located somewhere here inside the device, and of course this is the pointer coming out of it, the pointer coming from the PMMC. If you notice here, the range is in voltage. How to connect the voltmeter in the electrical circuit to measure the voltage? If I want to measure the voltage of this resistance in this circuit, I mean this resistance R1, to measure its voltage, we are going to connect the voltmeter at the terminal of the resistance we want to measure its voltage. For example, if I want to measure the voltage of the battery, I will bring the voltmeter. One terminal will be connected to the positive side and the negative terminal will be connected to the negative side to measure the voltage. Unlike the ammeter to be connected in series, voltmeter is connected in parallel. Of course, in the voltmeter here, we are including or we are using the PMMC, but we need other circuit with it because we agreed that PMMC can measure very small current. In that case, to be able to measure high voltage, we are going to connect another resistor in series with the PMMC. We call it the multiplier. Let us see this in the next slide.